Good morning and welcome back, nerds. Today we are going to finish our solving by square roots and completing this square lesson. We finished up yesterday by converting a standard form quadratic to vertex form. And that process is called completing the square. Just to recap, the reason why it's called completing the square is because you are trying to force a perfect square trinomial, which is one of these two things, to be present within your polynomial. That way you can factor it to a single set of parentheses squared, perfect squared trinomial. Awesome. So yeah, completing the square gets us from standard form to vertex form. I did tell you yesterday, though, that you always want to have the number 1, no other number, in front of x squared. This way your a squared is actually x squared. And this one, it fit that bill, so we were fine with that. But what happens if, boop, there is a number in front of x squared? Because the answer is, it's done slightly differently. You need a 1 in front of your x squared in order to complete the square. So yeah, we're going to do some kind of division, a special type of factoring. We are going to artificially segregate this piece of the polynomial. We are not factoring out a greatest common factor. We are literally just making sure that -3 is not in front of x squared by dividing that -3 out of that set of parentheses. Notice how wide I made my parentheses there. When I divide by -3, what I'm going to have left inside is a positive x squared, like I want at the front, and 12x divided by -3 is -4x. But like I said, notice how wide I left my parentheses. That's because the perfect square trinomial that we're trying to create will be inside those parentheses, and then they can be factored. Let's go ahead and put it at the top of the paper. Just reminding you that is the format of all perfect square trinomials. That tells us that that term in the middle is 2 times our b value because we can already see that a is going to be x. So this term in the middle is 2 times our b value. We know that 2b is -4. We isolate b so we can square it to figure out what number is going to finish off our perfect square trinomial. Divide both sides by 2. Then square both sides, and we'll find out that that b squared number that finishes our perfect square trinomial is the number +4. Now, we did this part yesterday. I put a +4 right here. But let me remind you, you're not actually allowed to change the equation. You're only allowed to manipulate the way it looks. That means just adding a 4 willy-nilly is not allowed. The only number you're ever allowed to just add with no punishments is 0, which is why yesterday we made sure we canceled that +4 with a -4. Up. This one did not have a number in front of the parentheses, though. You see, I know it looks like I added 4. I didn't. If you distribute this -3, we have to get back to our original equation. -3 times x squared is -3x squared. That's fine. That's there. -3 times -4x, that's +12x. That's fine. That's there. -3 times +4 is -12. And that's, oh, there's no -12 there. This would have created a -12. I'm not allowed to subtract 12. The only thing I'm allowed to do is add 0. So if this distribution creates a -12, what else do I need to do? I have to add 12. This is -12. That wasn't there before, so I will need to add 12 as well. Like that. This is our perfect square trinomial. That thing will factor The -3 is still chilling out front. But because it is a perfect square trinomial, I know it'll factor to something squared. The two numbers that multiply to 4 and add to -4 are this number and this number, just like they were yesterday. So that half of your middle term will always be what goes inside the factored parentheses. And 1 plus 12 is 13. Ta-da. Look, vertex form. Yay, vertex form. Not bad, right? I had someone in first period ask me why all of our stuff has a 4 in it and then a -2 in here. The reason why is because I'm trying not to give you a brand new equation. I'm trying to show you each time I do this thing, I'm just adding a little bit more to the idea. A little bit more to the idea. So I'm trying to keep stuff consistent. All right? This is the very first time that we're asked to solve by completing the square. We've already converted this to vertex form. It's on the other side of the notes. But I want you to see how the entire solving by completing the square process comes together. So we'll pretend we haven't converted this one to vertex form already yesterday. Is that a question for me? Just stretching. Okay. There's no number in front of x squared. So this is one of the easier ones. In order to get a perfect square trinomial, we're saying that this middle term is our 2b term. We then divide both sides by 2. We're cutting it in half. And then we're squaring, because all perfect square trinomials will end with a perfect square. This was not this number. That 5 was not this 4. So what we're going to do is we're going to write our quadratic with that plus 4 added in. But again, I'm not allowed to just add 4. The only number I'm allowed to add is 0. There, those two red things give me 0. I haven't actually changed the equation. But what I did do was find a perfect square trinomial within my quadratic. Because it's a perfect square trinomial, it will factor to a single set of parentheses quantity squared. The two numbers that multiply to 4 that add -4 will always be this value, quantity squared. And 5 minus 4 is +1. It's in vertex form. Yay, vertex form. Why do we say yay, vertex form? Because vertex form can be solved by using square roots. And PEMDAS in reverse order, SADMEP, getting x by itself. It says find the zeros. That literally means when y is 0. Just set your quadratic equal to 0 and start solving for x. No, we're not done. We're solving now. All completing the square does is convert it to vertex form. Okay? It doesn't actually solve anything. It just changes the format. Using square roots, though, that solves. Next, square roots, right? Square root both sides. But on the right side, it says square root of -1. Hey class, what's the square root of -1? Lots of voices. I. Awesome. And square roots cancel squares, which is going to create that plus or minus. You're finished when you isolate x, add 2 to both sides. Our two solutions are x equals 2 plus or minus I. There they are. Those are the solutions of this quadratic. And solutions like this, what do they tell you about the graph? The axis of symmetry is 2. Good. What else does this kind of solution tell us about the graph? Now, if we could actually plot that, we could say, yes, that my x-intercepts are I to the left and I to the right. But unfortunately, we can't plot those in the real number system. But if it was a number, let's just say it was like 2 plus or minus the square root of 3, then it would tell us that as well. And one more thing that this tells us, because it's complex, it doesn't touch the x-axis, which is why I can't plot them. Right? So look at all the information we know just from the way the answers are. So much stuff. We know the axis of symmetry. We would be able to identify where the zeros were in relation to the axis of symmetry if that was a real number. And because it's not a real number, we also know that this graph doesn't even touch the x-axis. X equals 2 is the axis of symmetry, yes. It doesn't touch the x-axis. This is the axis of symmetry. That's x equals 2, right? And can we agree that this quadratic points up because the front number is positive? It looks like this. It never touches the x-axis. It points up and doesn't touch x-axis, so I know its vertex is above the x-axis. We know so much about the graph without graphing it based on the answers. You would say no real solutions. We want to be really careful about when we start saying no solutions anymore, because in all actuality, there are solutions. They're just not real numbers. So if it was a multiple choice test, you could say none of these. That could be an option. But if one of my answer choices says no real solutions, this says there are no real solutions. So it's just understanding what the answers mean. What do you feel about the solving by completing the square process, which literally means convert standard form to vertex form and then solve vertex form by using square roots? That's what that means. Could you put the two skills together? I'll never say that these are fast, but what I will say is it should make a lot of sense. Let's do it again. This time, there's a number in front of x squared. So we're going to do the same thing we did in the first example of these notes. Like I said, artificially segregate a piece of this quadratic. That -3 cannot be sitting where it is. What I have to do is I have to divide it out of those green parentheses. You mean you've realized that the entire quadratic has a GCF? That's coincidental. So if the entire quadratic doesn't have a GCF, this process would still work. And that's why we only want to pull it from the front too. Okay? I should have made that a little bit wider because we know I'm going to have to squeeze a term in there. I'll just have to write not too large. We're dividing -3 away from both of these things. Dividing by a negative obviously is going to switch your sign. So you're going to get an x squared and a -4x. Should feel really familiar to you because you've seen this x squared minus 4x thing a ton of times in the notes. But it's because I'm trying to show you I'm at each step, I'm just introducing one more tiny nugget of knowledge. That's why. And in this one, I'm not actually introducing anything new. I'm just putting together all the concepts finally into one question. All right. That middle term, in order for this to be a perfect square trinomial, must have been double our b value. We cut that in half. We divide both sides by 2. We get that b is -2. All perfect square trinomials end with that plus b squared. So we will need to square this b. Of course, we already knew that was coming because we've done this one a billion times by now. That plus 4 goes in here, and it does finish off my perfect square trinomial. But I have just introduced a new value to this equation that didn't exist before, and the only new value I'm allowed to introduce is a 0. And I know it looks like plus 4, but it's not plus 4. If you did the distribution, it's not actually plus 4. It actually says minus 12. Because negative 3 times 4 is negative 12. My job is to make sure that it was 0. So whatever the opposite of this distribution would give me. This distribution happens to give me a negative 12. The opposite of that would be a positive 12. The thing in green parentheses is now a perfect square trinomial. I can factor it into a single set of parentheses squared. There is a negative 3 hanging out on the front, a vertical stretch and a reflection over the x-axis, whatever. And we've already seen this several times, but the two numbers that multiply to 4 and add to negative 4 will be this number twice. And since it's twice, I get to write it as one set of parentheses squared. Negative 9 plus 12 is 3. There. It's in vertex form. Just like last time. Now that it is in vertex form, I have the ability to solve by square roots. It says find the zeros, that means solutions, but we call them zeros because literally y is 0. And now solve using square roots. And I should have written that in purple like I did last time. Shuck, shoot, darn. I'll start writing in purple from now on when I'm writing this now. But getting x by itself, what's the first thing you're going to do? Add 3. Subtract 3. Like that. I have a negative 3 on the front. X minus 2 quantity squared equals negative 3. Next. Yep, now we need to divide by that negative 3. That gives me x minus 2 squared equals 1. Man, that feels familiar. X minus 2 squared equals 1. It feels so familiar. I mean, it's like, it's darn near this one. Look at that. It's almost the same thing. The only difference was it equals positive 1 on that side, not negative 1. So when I take the square root, I am not going to have to goof around with imaginary answers and complex results. But you do need to remember the plus or minus. Don't you be forgetting the plus or minus. We got x minus 2 equals plus or minus 1, because the square root of 1 is 1. Reminding you, the two setups. X minus 2 is negative 1. X minus 2 is positive 1. And you're just going to add 2 to both sides to isolate your x's. We get x equals 1 and x equals 3. Again, we know a lot about our answers, or a lot from our answers, excuse me. We know that the answers are 2 plus or minus 1, so we know the axis of symmetry is x equals 2. We know our answers are 1 to the right and 1 to the left of x equals 2. Because we got 2 solutions, we know that this graph actually goes through the x-axis. Because the front number is negative, I know, I'm sorry. She asked about the plus or minus, where the negative one comes from. It's the negative one. See, here's the plus and here's the minus 1. And then the last thing I was saying, because I know I have 2 solutions, but I also know that are positive, and I know that this graph points down, I know that it looks like this. We know so much just from looking at the answers and the equation about the graph itself. So much knowledge is tied together in this. So what do you think overall about the solving by completing the square process, which involves taking standard form, converting it to vertex form, then solving vertex form by setting equal to 0 and using square roots and PIMDOTs in reverse order. What do you think about as a process? Is it doable? Does every step make mathematical sense? Not like, oh, you've memorized my pattern, but every step I've showed you why this is working. I've showed you plenty of times how to factor, why that's working. We've solved using SADMEP a billion times. Does it all come together and make sense? I'm going to be honest with you. Solving by completing the square is the method for solving all quadratics. It's the method. Look how powerful it is. It can turn any standard form into vertex form. And all vertex form can be solved by using square roots. Donald, you look like you almost had a question and then... Because it's not, he wants to know why we have to know the other versions with the other possible ways. Because it's not the fastest, bless you. So yes, it's powerful. And it'll do a lot of stuff for us, but is it my go-to method? No. It's a method that I use under very specific circumstances because of look how much work it requires. Because honestly, I could have factored this much faster than all of this work. Because like, whatever her name is, what Melissa asked, what about negative 3 GCF? You see, the very first thing I would have done is I would have seen that I could divide all these by negative 3. And that would have given me a negative 4 here and a positive 3 here. And I would have said, are there two numbers that multiply to 3 that add to negative 4? The answer is yes. I can factor this. And I would have gotten to the answers much faster. I'll tell you what I never do. I never solve by graphing. I never do that one unless I'm using my graphing calculator. So solving by graphing is a great process if you have a graphing calculator. Otherwise, it's too unreliable with consistency. You know, did you have a graph paper? Did you graph it perfectly? Were the answers pretty? Like there's too much going on, you know? So factoring is my go-to, and I only use completing the square under extremely specific circumstances. I'll explain those extremely specific circumstances after one more example where we do this process, okay? Another thing that's great about solving by completing the square is you don't need it to be set equal to 0 to pull it off. You just need to be able to convert any standard form equation to vertex form. Can't have that 2 sitting in front of my x squared. But this 1 that's over here, it's fine. Let it chill, whatever, not a big deal. I need to divide that 2 out of those parentheses. When I divide 2 out of the parentheses, it'll leave me x squared plus 6x. I'm trying to force a perfect square trinomial to occur inside the green parentheses. The only way that can happen is if the middle term, 6, was actually our 2b. Because remember, a is x. That means we need that middle term to be 2b. Figure out what b is because we're going to have to square it to finish off the perfect square trinomial. Divide both sides by 2. Then square it. Okay. A 9 will finish off my perfect square trinomial. And I know it looks like I added 9, but what did I actually do? I added 18. Because if we distribute this 2, that would have said plus 18. So what else do I need out here? Minus 18, because 0 is the only number I'm allowed to add. And now my red things, along with a little bit of distribution, will get me the 0 that I needed. Because we engineered the perfect square trinomial, we know that green set of parentheses will factor to a single set of parentheses squared. And if we did it right, this will always be the number we find inside those parentheses. Let's check. The two numbers that multiply to 9 and add to 6. Yup, 3 two different times. Oh, and by the way, negative 9 minus 18 is negative 27. Vertex form is set equal to a number. You see, vertex form can be set equal to a number to solve. Solving by factoring can't. Solving by graphing could, if you want to graph more than one thing. But solving by roots, or even using completing the square and then by roots, whatever, be equal to whatever you want it to be. As long as you could use PEMDAS in reverse order to isolate an x. What are we going to do first? Yeah, we're going to add 27. I'll remember to write in purple this time. I can't cancel the square because there's a 2 in front of the parentheses. But I can cancel that multiplication with a division. Ba-doop. We take the square root of both sides. Bless you. And we remember that canceling a square with a square root creates a plus or minus. And 14 actually doesn't clean up. You can't divide 14 by any perfect squares. It's 2 times 7. So I'm going to have to leave it as square root of 14. Yes, Max? Because if I distribute this 2 to this 9, there'd be a brand new plus 18 that didn't exist anywhere. So this was me making sure that I actually don't have a plus 18. I actually only have a plus 0. Lastly, subtract 3 from both sides, and your two solutions are x equals 3 plus the square root of 14 and 3 minus the square root of 14. Ta-duh. Yes, it would be negative 3. Good thing I left myself a space. Someone in first period, I actually heard her whisper that she likes this because it's easy. And I chuckled. And the reason why I chuckled is because it only seems easy because I only gave you the easy ones. Remember, I told you that I only use solving by completing the square under very specific circumstances. And I made sure that the only examples you saw satisfy my very specific circumstances. First of all, rule number 1, if I see any fractions in my equation at all, I don't even bother. Could I do it? I could. I could solve all quadratics this way. I don't bother, though, if there's fractions. Another method. Rule number 2. The middle term must be even after I've divided by the front number. Look, 12 divided by this 2 leaves me a 6 on the front. 12 divided by negative 3 leaves me a negative 4. Because if I get an odd number after I do that division, I'm going to get a fraction the moment I try to get to this step. And now I'm squaring fractions. And now I'm finding least common denominators. Could it be done? Yes, it can be done. So, rule number 1, if I see fractions anywhere in it, I mean, I could cancel the fractions by multiplying by the denominator or whatever. But honestly, at that point, I've already done more work than I wanted to. I would have used a different method. Rule number 2, I just check in my mind real quick. If I have to divide away this number, and say this number's a 1 right here. If this number's not even, I don't mess with it. For the same reason why if I do have to divide, if I don't get an even, I don't mess with it. So yeah, there are times when I'll go to use completing the square. My go-to method is factoring. If I can't see that it factors real quickly in my mind, Then I ask myself, is it worth bothering completing the square? And if the answer to that question is no, and I'm not allowed to use a graphing calculator, then I have to default to another method. So, my phone is not on vibrate. I am now going to show you something at the bottom of these notes. I'm going to show you how powerful converting to vertex form and solving by square roots can be. I'm going to solve a quadratic in standard form that has no numbers in it. What I need from you is I need you to pay close attention and just understand the logic and the math behind every step. I'm never going to ask you to recreate this. But I'm telling you, knowing what I'm about to show you is big time important. And as far as I'm concerned, it's one of the most important things I'm going to show you this year. Nothing new is about to happen. I'm only going to use completing the square to get this to vertex form, and then I'm going to solve my vertex form by square roots. So absolutely nothing new. Just no numbers. All right? Here we go. Oh, by the way, I'm not going to write this 2b squared thing because I don't want you to confuse it with the b value that's sitting here right now. Okay, first and foremost. Oh, and also don't write large. I can't have a number in front of x squared since I'm trying to complete the square to convert this to vertex form. What I have to do then is I have to factor that a out. I have to divide that a out of these parentheses. When I do, it gives me an x squared. And since I don't know the value of b and I don't know the value of a, when I divide b by a, I'm going to have a fraction. Plus c is still hanging out over here. Oops. Sorry. Don't put an equal sign there like I just did. Just leave it alone for a minute. Because you know we're about to put a number there. And then we're going to have to cancel that number out here. This thing, this b over a, we know that it's double what I need in order to complete my perfect square trinomial, right? So normally you see me divide by 2, but it's already a fraction. So instead of dividing by 2, what can I do? No, what I'm saying is, what's the same thing as saying divide by 2? Multiply by a half. So what I'm going to do is I'm going to take my b over a, and I'm going to multiply it by 1 over 2. This is going to give me b over 2a. What we've done every other question is we've squared that thing to finish off our perfect square trinomial. So if you square it, it squares the top and it squares the bottom. So it squares the 2 and the a. I should have made my parentheses larger. Now I know it looks like I've added a b squared over 4a squared, but I didn't, because I could do this distribution. I'm going to do this distribution off to the side over here just so you can see what would happen. When you multiply this a to this red thing, what you get is this. A times b squared over 4a squared. But this fraction will reduce because it has an a on the top and it has a's on the bottom. This a gets rid of one of the two a's on the bottom. So there will only be one remaining. So I know it looks like I added b squared over 4a squared. No, what I actually added was b squared over 4a. So in order to cancel that, I have to say minus b squared over 4a. Do you see so far that I've done everything exactly the same as I've done with the other questions? It's just that right now I don't have numbers to work with. So far, so good. Remember, I'm not asking you to reproduce this. I'm just asking you to understand each step is the exact same math that I showed you with letters instead of numbers. That was this distribution. See, here I was able to just do it in my mind and say, oh, this 2 times this 9 would have been an 18. But here, I didn't want to try to ask you guys to do it in your mind and then cancel. I wanted you to see it happening, to see why I'm using the opposite of this out here. Okay. Now, the perfect square trinomial is complete. Oh, that's where the equal 0 goes. The perfect square trinomial is complete. The thing inside the parentheses can now factor. And because I know we did it right, every single time, do you remember what I told you would end up in those parentheses? It'd be the value after it was cut in half. And oh, you know what? I don't. This kind of bothers me out here. I don't want to see 2 different things out here because every time I've done this, there's only one thing, right? Tell you what we're going to do. Let's make this one thing. Let's write it as a single fraction. Right now it says c over 1, and I'm trying to subtract b squared over 4a. These 2 fractions don't have a common denominator yet. But what's the least common denominator? 4a. Well, this already has 4a. So this one just needs me to multiply by 4a on the top and bottom. When I do, they'll have the same denominator, right? The denominator is 4a, but the top will say 4ac minus b squared. So I was just combining my 2 terms. Whew, there's a lot of crap going on here, isn't there? Hey, wait a minute. If I just finished completing the square, this is vertex form. What's the x value of the vertex? X equals, from this, x equals negative. Remember, you have to use the opposite symbols. What makes the inside equal 0? What makes the inside equal 0? X equals negative b over 2a. I feel like I've heard x equals negative b over 2a somewhere before. Oh, that's right. That's the formula we use to find the axis of symmetry of standard form. That's why we get x equals negative b over 2a. How about that? It wasn't just made up. It was found doing this. So cool. By the way, that means this is the vertex, the y value of the vertex, when it's in standard form, if you cared to memorize it. Or you could just plug in whatever you got for x equals negative b over 2a. That's what I do. Okay, let's go ahead and solve using square roots now. Uh-oh. Wait, what day is it today? Uh-oh, I only have 5 minutes left. Okay, I'm going to subtract this over to the other side, like that. And I'm going to try to save a little bit of space here because, well, no, I'll just write it off to the side. So minus this fraction. I just can't. I don't know. Just something about this really, really bothers me. I don't want to see that minus sign in front of that fraction, especially because there's a minus sign already up here. So you know what I'm going to do? I'm going to actually say that this is, remember I told you that that negative sign is either going to the top or the bottom? So tell you what I'm going to do. I'm going to say that this actually says this. And when I distribute that negative 1, this b squared is now positive, but this 4ac is now negative. Okay, that feels better. That's just prettier to look at. All right. once we got to this point in our solving by square roots, every time we divided by this a value, right? But there's already a fraction, so instead of saying divide by a, what else could I have said? No, instead of saying divide by a, I could have said multiply by 1 over a. So multiply both sides by 1 over a, and what you get is x plus b over 2a squared is b squared minus 4ac all over 4a squared. Because you just multiply the two a's. We need to cancel our square, don't we? Don't pack up, I got time. Oh, that's going to create a plus or minus. Also, did you know that when you take the square root of a fraction, you're taking the square root of the top and the square root of the bottom? Did you know that? Well, now you do. Unfortunately, the square root of the top is not pretty, so we'll just leave it as b squared minus 4ac. But on the bottom, 4 is a perfect square. The square root of that is 2. And a squared is a perfect square. The square root of that is a. And the last thing we need to do to get x alone is subtract b over 2a from both sides. Bless you. So it gives me x equals negative b over 2a plus or minus square root of b squared minus 4ac all over 2a. And by golly, they have the same denominator? And I'll just say that negative sign is part of the b. X equals negative b plus or minus root b squared minus 4ac all over 2a. Quadratic formula. That's what's up.